Hi, everyone. My name is Randy Stott. I'm the managing editor of Gear Technology and Power Transmission Engineering magazines. I'd like to welcome all of you to the first ever session of Ask the Expert Live. And today we've assembled a panel of experts, all of whom are specialists in gear grinding. So today's topic is gear grinding, and here to answer your questions. This is an audience participation event. We would love to have you ask questions and participate. Even if you don't, it's a great opportunity to sit down and learn some things about gear grinding. If you're a little bit bashful out in the audience, I do have some questions from our readers and our website visitors, but it's going to work a lot better, and we would prefer if you guys would ask the questions and get the knowledge that you need. Here's how it works. If you have a question, just raise your hand. I'll hand you the mic. You can introduce yourself, ask the question, and then the experts will provide the answers. But before we get started, I'd like to give each of these gentlemen an opportunity to introduce himself. So if you don't mind, starting with Harald.
This works, okay.
Maybe that's working.
My name is Harald Gehlen. I'm with the company Reissauer in Switzerland, Zurich. And I'm responsible for the application engineering. And we build machines. We build mainly gear grinding machines, mainly gear generating grinding machines. Half of my life I spent already in the gear business. I started with the studying in Aachen, mechanical engineering at the university in Aachen. Then I went to Powder, now Gleason Powder, for about 10 years. Afterwards, I changed to Oerlikon Geartech, profile grinding machines. And now I found finally the one I'm looking for, company Reissauer.
So nice to meet you. My name is Enrico Landi. I'm in the gear business working for Sampo Tensili company that we are here in US represented with our joint venture Star SU. And I'm responsible for the division of producing grinding machines, mainly profile grinding and generating grinding machines for cylindrical gears.
Yeah, this works. Use that, it's better.
Okay, I want to use this mic. I think it's a little bit better so that we have sound interference with the hand mic. My name is Andreas Mehr. I'm the technology guy at Liebherr for gear shaping and grinding. That means today you also can ask me some grinding questions. I study mechanical engineering at Karlsruhe, in the University of Karlsruhe, so that not everybody who knows about gears is coming from Aachen. Therefore, some other guys in the world are sitting here. And I work for Liebherr since 2004. And beside the technology expert, I'm also the head of our test department at Liebherr Gear Kempten. We make the hopping, the shaping, and also the gear grinding machines.
My name is Dr. Hermann Stadtfeld, and my speaker before is partially wrong. Most people come from Aachen, like myself. I made my master's degree, my PhD also at the Aachen University. Then had my first industrial years at Oerlikon in Switzerland. Then I went to the United States. Had to bridge a time of 1 or 2 years where I was a visiting professor at the Rochester Institute of Technology. And then I started my job assignment at the Gleason Corporation as a director of R&D. Today I'm vice president of Bevel Gear Technology. And as such I'm responsible for bevel gear developments, but also many cylindrical gear developments, like for example some aspects of the power skiving. And if you read Gear Technology magazine, in the meantime I have become the go-to person for worm and worm gear questions as well.
Thank you, gentlemen. Now, who's got a question on gear grinding? We're going to start then with one from our readers. And so the question is, what grinding parameters affect the risk of grind temper? Anyone? Harold, go ahead.
Okay, there's a lot of things which affects the grinding burn, and I think our target from our side must be to avoid everything what grinding burn is creating, because the grinding burn is bad for the workpieces, because the residual stress becomes smaller and even goes into the tensile strength. Okay, there are different things. Of course, the material itself is very, very interesting, and also the hardening of the part is very, very important. But also the conditions which we use for the gear grinding is, of course, very important. And you can say the feed rate, you can say the grinding speed, the in-feed, the stock removal, everything can affect the grinding burn. And we have the target to optimize this process this way that no grinding burn occurs. And I think we are able to do that. But also the grinding wheel itself and the combination between the grinding wheel and the dressing tool is very important. The grid size, the specification of the grinding wheel, also the grid size of the diamond tools is very important. You can make a gear very, very smooth by choosing the right dressing parameters, and this can create, of course, also grinding burn. And because I know that the grinding wheel itself has also a big influence, because we differ between, for example, the Corundum grinding wheel, the CBN grinding wheel, and the CBN has, of course, slight advantages regarding the grinding burn. And because of that, we decided also to make our own grinding wheels, to have much more influence on these specifications.
Anybody else? Enrico.
Yeah, just agree with what he's saying. Just add that being a thermal damage an issue related to the energy produced by the process itself, it's very important to consider that this energy is depending by the cutting forces, by the contact time of the wheel with the part, and by the cutting speed. So at the end, considering all the process parameters that are, let's say, influencing the contact time and the cutting forces, these are the ones that are related to the, let's say, try to keep this process under control, avoiding thermal damage. I would point out, if I have to choose two main parameters in this case, are the radial in-feed for sure, as well as the cutting speed, which are mainly affecting this process. Of course, all the things related to the tooling are going directly inside the value of the cutting forces. So that's the point.
What do you think? Is it the smaller cutting speed which creates grinding burn, or the higher cutting speed?
Higher. But even if it is something that we have also to evaluate the contact time, each parameter has some influences that can be positive in a way, but negative in the other way. So if you grind with a higher cutting speed, this can influence the energy related to the surface contact area, but on the other side, reduce the contact time that is between the wheel and the gear. So it's not a direct effect, can be sometimes related to also other parameters.
Can I? Bevel people are not really known for getting straight to the point, but I like to summarize that because everyone said the right thing. For somebody who was looking for a plain, simple answer, it's the consistency in the specification of the grinding wheel, and it's the consistency in specification structure of the workpiece, the speeds and feeds, and the coolant, as well as the coolant access. There is one comment I like to make to the last speaker, which is, or to the comment he made. Sometimes, when you run the grinding wheel faster, like we say when you run it between 4 and 6 meters per minute faster, the grinding wheel acts like it was a crate harder. And those things have to be considered, because if you are at a borderline scenario, running it a little faster in some cases avoids your burn. So it's sometimes the opposite conclusion may be right. But in principle, it's the workpiece, the grinding wheel, how the grinding wheel is stressed, how the coolant access is, and what kind of coolant you use. And speeds and feeds, of course.
Along the same lines, the same reader asked if it's true that gears with high retained austenite are at increased risk of grinding temper.
I was actually looking into that. I had a discussion with our metallurgist at Gleason Works, and there is not really a history that retained austenite would increase the grinding temper or even cause some grinding burn. Normally, it depends on what the structure looks like. If it is on the surface in a small layer, you grind it away anyway. And so there is not really any history known that I know of, and that metallurgists have reported that the retained austenite has an influence on the grind temper.
So we made the improvement that the retained austenite is could be 10% to 20% without any impact on the grinding burn, but below 30% and even more, this could create grinding burn. These are the numbers we have in our company established.
And I mean, if you're above 50%, you really didn't harden your part properly anyway, right?
Yeah. That's right. You do something with the hardening
Don't got no
process.
martensite then.
We have a question from the audience.
My question is, what are the best conditions, or what are the parameters to find a reasonable compromise in between a sharp grinding wheel, which is able to cut, to make a lot of removal without danger of grinding burns, and on the other side, a smooth surface finish for improving the gear efficiency? What are the parameters from your point of view that should be taken into account?
Andreas?
As already said from the other speakers, is I think the most, in my opinion, the most important point is that you find the right grid size and the structure of your wheel. The dressing parameters on, let's say, on generation grinding, the speed ratio is not so important as you know it maybe from profile grinding, and therefore you have always already in the dressing parameters a contact of the complete tooth profile of the grinding worm. Also the generating grinding effect is different. Therefore it's very important to find the combination between your grid size, the porosity of the wheel, that means how many bonding you bring in to create this, and how this wheel reacts. What Dr. Stadtfeld already said, if you grind a little bit faster with this wheel, it reacts harder, and maybe this will help. And this is then the situation when everybody said, oops, I have grinder burn, I slow down the speed and the feeds to remove it, and then they end up and say, oh, it's much more terrible. So that the contact condition is very, very important between the abrasive and the material itself.
And Dr. Müller, that question is really, in today's spirit of the modern grinding wheel technology, it's difficult to answer. I had just a couple of weeks ago discussion with a customer that run on a grinding machine. They run a Cubitron that has a 40% mix with conventional grinding material. And they run it with 40 to 50 meter. And there's not the grind burn, there was a surface finish thing. And they had some noise issues or some surface finish issues. And actually we said, yeah, right, you run it with 50 meters, what do you think? And he said, no, that's not the problem. We have 4 or 5 machines running with similar parameters, and they are fine. And actually we discovered the problem, some were completely different, had nothing to do with the grinding wheel. And it was relatively open port rest, but the secret was this new magic mixture. And I think with those new grinding materials, we really enter slowly but sure, maybe more slowly, because people had high expectations, and at the beginning they were not really fulfilled. But with those mixed grinding wheels, those hybrids, I think we enter a new world of grinding technology.
Anyway, one consideration, if I can add, typically to avoid the grinding burn is the roughing process that have to be kept under control. So wherever you're looking for a fine finishing on the roughness of the gear, you are going to choose a certain type of wheel, but you cannot expect that it is the good wheel to avoid a burning that would happen in the roughing process typically. So also some new approaches in the last period that have been seen on different machinery are to avoid this compromise of the choice of the wheel that have to be done to have a proper roughing process and a good roughness at the end with the finishing process.
Very good, thank you. Next question comes from a reader. Oh, we got one from the audience. Joe Arvin.
Mine is not a question necessarily. I just like to add a couple of points that I feel is relevant to the question. One, there are copious reasons why, as was said by the speakers, of causing burns. And as Dr. Stockfeld said, the coolant. I'd like to add 3 things. One, the coolant must be kept clean so you don't have the swarf coming back through the part. Number 2, if the part is magnetized, it will adhere the swarf back into or hold it on the part and cause burns. Number 3, the diamonds themselves, as they wear, they no longer cut freely, but they actually crush away the wheel, and that can cause tempering. Thank you.
Thank you, Joe. Next question from a reader. Can the accuracy of inspection be trusted if it is done on the grinding machine, or does it need to be inspected on an independent CMM? Harold?
I think it can be trusted because you can measure this part on the same machine. The only difference is that you use the same axis or some of the same axis for the checking. And this is, I think, not a certified inspection, but from our opinion and from our experience, we see that we can be within DIN class 2, within 2 DIN classes in tolerance.
I would just also place another comment on which I agree with your position that the axes of the measuring machine are different to the axes of the grinding machine, and this particularly affects the lead measurement, not the profile measurement. That's one point. So if we look at the profile measurement, this could be for sure more accurate or more similar to what we can see on a measuring machine. The other thing to be considered is that typically on a grinding machine you measure the part which is still clamped. So depending on the geometry of the part, the condition of the part itself on a measuring machine and on the grinding machine is completely different. And in this case, the result on a grinding machine could be even better than what it is at the end on the final part.
Because you don't have the influence of the clamping fixture.
Exactly.
Now, how that is, right? The experts, the answers, some of the answers should confuse you so much that they cancel out. I'm giving another answer. I think if you measure in a cutting or grinding machine, you got heat and swarf and other things. Of course, you can cover your grinding probe up, and you can, after you ground the part, wait an hour and a half until it cools down and gets a normal ambient room temperature, which it doesn't have after grinding, and to then do the measurement. My opinion is, and that's maybe a philosophical standpoint, In a machine with all the dust and the heat and so on, you can measure the part immediately after grinding or cutting. In order to stock mapping, if you have the stock allowance, you can also do a spacing, probably very precise. When you do a flank surface measurement, in order to make first, second order corrections, I think that you'll be not in the range of a DIN 2, you maybe be in the range of a DIN 6 or something like that, or 7, but that's good enough to qualify the first part. I would not think that the onboard measurement, and we do it for grinding and cutting, should replace a real CMM in a temperature-controlled room.
To add this also, because it was mentioned that is a philosophy, at Liebherr we can say we do not call it onboard measurement, because measurement is something what we have to do in a temperature stable, clean area. The part already is crowned with oil. You can spin it on the table so that the most swarf and oil is gone away. And we called it onboard inspection, and we use it for a setup for the operator, so that maybe after dressing you have to inspect if the profile angle is okay, the slope, and then you can say yes, the slope is within my tolerance of plus minus 5 microns or maybe 7 microns I need for production start, so that I do not have to wait until the diagram is measured in the inspection room and bring back to the machine. I can start the production, I know I'm in quality, and the last microns, that's my opinion, I have to bring out of the measuring room. Especially if you want to check the profile form deviation with oil, without oil, that's more than a few microns that you measure on this oil film.
Thank you all. Next one is a little bit complicated, so stay with me here. If a gear is form ground and has lead modification produced by radial feed of the grinding wheel, will the profile be accurate at all positions along the tooth flank?
No.
No.
Simple answer, no.
No.
Can you explain
If it's a spur gear, yes.
Right. As soon as you have a helical gear, you get twist in, and if you measure different positions. However, the question probably can move on one step. There is twist compensation, so you could correct them, and afterwards you can also produce a helical gear very precise. But it would have to take care about the fact that if you only make a length modification for crowning, you'll get a twist, and that can be eliminated.
Can you explain to the audience a little bit what is helical twist and why it's a concern?
Related to which process?
Maybe we have a picture. Maybe we have a
You know what,
to show.
Randy, I was asking for a flip chart. There is none.
No, but we have a slide.
I can.
We have a
Okay,
slide.
you have a slide?
I tried in another situation. The situation is the following. This is my lead. Yeah, that's the lead. I want to make a crowning like this. And if I make this crowning, I get the twist for profile grinding, and I get a twist, let's say, for generation grinding. And to handle this twist, you have different possibilities, also on profile and generic grinding, that normally what the gear designer expect, that the crowning and the position and everything on every position, the profile looks okay. Now this is what we are doing. When we create a crown with a center distance, we create a twist on the top and the over bottom. That's all.
Yeah, the generating line is not rating length is. You move the grinding wheel along the part with an infeed, and this creates the twist.
I shouldn't have asked for that. I shouldn't have asked for that. But anyway, if you had a helical tooth, then I'd probably ask the impossible for a second color. As you go along the face width, for example, a grinding wheel would now ride in a circle, and it would produce a slightly circular root line, and that's done via the pressure angle. So it would produce a root line like that. And via the pressure angle, the grinding wheel is at the one end lower down, and at the other end lower down, and in the middle it's, for example, higher. And as the grinding wheel goes down, it takes more stock on the sides, so we get this length grounding. Now the length grounding would now cause, on this gear, if it's a helical gear, in a straight gear, it goes straight in axis direction and there is no side effect. And if you have a helical gear, you get, for example, stock on condition there, an additional one, additional to the length grounding, and you get something like that. So now, and if you measure here, this should actually go through the middle. And if you measure here, so if you measure lead-in profile in the middle, you don't see it. You would have to make additional measurements here, 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 and here, and then you will see in your profile check, you will see in your profile check, you see something like that, that. In the middle it's none, and on the other side it gets larger. And that's the twist, and that's like the winding of the piece of paper, like was shown before. And that can be eliminated now with either with additional motion, single side, or even completing with certain tricks. And I think most of the manufacturer, Gleason also, has some patented approach to eliminate twist.
Thank you. Next question. What is the best way to document the stock removed by grinding?
The best way is to go back to the systems we were mentioning before, so an inspection that we could do before the grinding process and after the grinding process. So with the inspection units, you can certify and document what you have cut piece per piece. That's thinking and not high production systems, of course.
Like in aircraft, a stock mapping is done before you grind the part, and then the stock is evenly split between the two sides, and after the grinding, the measurement is repeated, and then, for example, 75% of the stock is taken off, and you take the other 25% off. It's like a measurement on the machine, only with the intention, but more than on one point. It looks at several points on the flank.
And if this is not even, left and right flank, then it's difficult to say.
You know, yeah, that's difficult, yeah, because you never know. The final ground geometry should probably be the nominal geometry. So that means your soft manufacturing. So you would have to average, to try to average it in or get a best fit between the surface before and the surface after.
Yeah, but you could do the check before and then the check afterwards, and also take into account the encoder of this axis, of the workpiece axis. And then you have the real amount of stock on the right flank and the left flank.
What did I say?
Okay.
Question from the audience.
It's not really a question, it's just an amendment. You discussed before the possibility of onboard inspection, and I think onboard inspection is the only reasonable thing to document the machine. If you would do it on a CMM outside of the machine, you lose somehow the reference, how much was on the left flank, how much on the right flank. And the other thing, and that's quite important, is of course you have an error because no axes are really rectangular or parallel, but it's a comparison between probing before grinding and probing after grinding. So if we assume the error will stay, and since we just take into account the difference, we are very precise in an onboard inspection concerning the stock removal.
Yeah, it's a good statement.
Thank you very much. Gentlemen, which is the best method for detecting grind temper? Surface temper edge, Barkhausen noise analysis? Which works best?
Etching is the best. But I mean, in production, in process, the Barkhausen is the way to go often, because you can do 100% and so on. But still then, most manufacturers go with a percentage of their parts. They go still for etching. An aircraft manufacturer would not get rid of the etching versus Barkhausen.
Edging is the most used one, but it's also the most sensitive to how it is done, the edging. So the Barkhausen is, on a certain point of view, is more scientific approach. And similar to the comment of measuring, it's really easy to have a good part with the Barkhausen feedback and the measured part that make a reference to this. So in this way, we are, let's say, more safe as a result, rather than with the edging.
Yeah, with the nitro check, you have a whole check for everything. With the Barkhausen check, you have just maybe one flank or just one line, and doesn't give all the part.
Very good. Next, one from the audience.
I'm not familiar with the latest of the Barkhausen approach for checking for tempering. However, my last read on this, it couldn't do the root radius, and it was hard to do all of the tooth flank and all of the lead, or the width of the tooth. Can someone tell me I'm wrong on that, that now they can do check for root radius burns and full length of the tooth lead?
I think it's always a question as how the sensor looks like. Our colleagues at Biberach, or also our aerospace group, they use Barkhausen as a very good method. They inspect it directly on an inspection machine, that you get some lines over the complete flank on the tip area, reference diameter close to the root, and if you want to measure in the root, you have to change the probe, that you also get a root that you can drive along this root. The situation often is on this gear is they are hopped, you have a feed mark still in the root, but the customer did not grind the root, and therefore you have a measurement with this probe which crosses the feed marks, and this will also have an influence on your signal. Therefore it's really not so easy to measure directly the root, or also from the involute to the root area, this section. Right.
Sorry about that.
Joe, we have that also on bevel machines. Joe, we have that also on GMS machines for measuring cylindrical and bevel gears. And it is basically like this aircraft measurement. The probe is automatically changed, and the Barkhausen probe is like a measurement probe. It is moved in areas. So if you make fine enough lines, if you have a fine enough resolution, and you take yourself time, you could measure the entire route. Only people go and limit that, kind of find a good compromise between the measurement time and the area that they like to measure. But the probe can be moved really in lines like a measurement probe in the root fillet. Oh, I wouldn't know if you measure the entire route. If you really want to measure the entire route of a Module 5 gear, you probably add the entire route, you add 5 minutes. So you add a time that's longer than the original measurement time. But if you go only to the critical spots, which most people do, because they etch anyway, and they kind of get like using the etching as a reference, as a calibration, then you go only to the critical areas, you do it in less than half a minute, and you still capture the most important information.
Thank you, gentlemen. Next question. Is there any way to rework grind steps short of full root grinding?
Can you repeat the question?
Is there any way to rework grinding steps short of full root grinding?
I don't think you should have any grind steps. I think now talking for bevel gears, you dress your grinding wheel, you have a semi-finish strategy. You cut a little deeper, then you grind, so you don't grind the root. That's where the step could come from. Then you have a root fillet radius in the soft cutting, That's a little bit smaller than the root fillet radius that is stressed on the grinding wheel. Then you have a protuberance on the soft cutting that fades off to the root fillet and maybe relieves 75% of the stock allowance, but not 100%. Now you make the first grind. You grind, let's say, a first slot, and you see that you took a little hard on the coast side and a little bit less on the drive side. That's something that with the eye you can sense very well, but you could do it with a measurement machine or contracer. Then you balance the grinding wheel. That means you give to the stock division a certain offset value, because you say the coast side needs to blend nicer or the drive side needs to blend nicer. So, and then you grind the part, and you never will have a grind step. You have a smooth blend into the root fillet that, in the ideal case, ends going afterwards in. Some aircraft people do that for certain purposes, but I think in spiral bevel grinding it's very uncommon. It can be done in one step if the chain of different processes is chosen right.
Very good. How do you make sure you have the thickest tooth to start grinding on?
For generation grinding, it's very easy because you make at the beginning, you make your stock alignment with a mobile meshing sensor. Therefore, you get a complete message out of the gear, and normally that's from the principle of generating grinding. You start with an in-feed, and then the part turns with a high speed. That means you start already with the highest amount of stock to cut this away during your in-feed, and also over the axial feed. And that's very often the reason, if you stand in front of a generation gear grinding machine, that you see a firing spot depending on the run out, firing, no firing, firing, no firing, depending on the run out, which is already on the part. It's a little bit different on profile grinding, where you have to find this highest point so that you do not overload the gap or grind too much with your grinding disc in there.
There you have to check the part inside the machine.
I have a question from the audience.
Good morning, gentlemen. Can you give me a little discourse on why you would want to use dressable CBN versus traditional plated CBN wheel?
Yes.
General or for some parts is the question is referred to which type of production?
General gear grinding or
General gear grinding?
General gear grinding, or even thread grinding.
I think CBN is one of the grinding wheels which has the lowest or highest thermal conductivity. So the grinding heat which appears will go a lot of the heat will go to the grinding wheel, into the grinding wheel. And I think this is one of the main reasons that the CBN is a better grinding specification. But it has also disadvantages, of course.
Talk about the difference between plated CBN and dressable CBN, if this was the question, maybe. I also got this point. The advantage of the dressable CBN is, of course, the possibility to perform modifications once the wheel is already in the machine, and this gives a lot of better flexibility in defining the part rather than replating or correcting the wheel since the beginning. And this gives also the possibility to use small size of wheel. And this is valid also for the plated CBN. Because in ceramic you wouldn't have enough materials in some cases to have enough dressable wheel to perform some applications. So CBN is very good in this case.
Only to complete, there is not really any bevel gear grinding done with CBN wheels. We use CBN wheels for for example, for plate grinding, they are traceable. But in the bevel gear grinding, we have a special situation with straight bevel gears and face gears, where we use non-traceable, permanently coated, galvanically coated CBN wheels. But that's only, let's say, because of the possibility to use a traceable, ceramically bound traceable wheel is not given for straight bevel gears, because you have very fine discs and you couldn't press them to the side because then you immediately lose blade point, and you couldn't press them radially because then you change the geometry. So we have, in bevel grinding, we use generally to 100% ceramically bound traceable grinding materials. Of course, different, those new modern wheels, but not CBN. And only in cases like straight bevel gears and face gears, those are those are permanently coated CBN wheels, where the face gear wheels even have an involute on the profile. And there's exactly that problem, that if you have to change something with the involute, you got to strip the wheel, modify it, and then recode it.
Just add another comment, sorry, regarding the roughness. So with the plated CBN wheel, for example, if we think about profile grinding, you reach a certain roughness depending on the grit size that you have chosen on the wheel. And typically to go on roughness that are below 0.8, like 0.6 or 0.4, you need two different types of wheel, like roughing and finishing, while on the CBN dressable wheel, you could reach similar results by just using one wheel and dressing with different methods in roughing and finishing. That's an advantage.
The situation on generation grinding is when we decide to go for, let's say, electroplated CBN or dressable CBN, is if we have a restricted tool overrun, that means we need small worm diameters. And then the question is, between dressable ones and electroplated, when we have a tool diameter maybe only of a worm of 80 millimeter, then is really the question, what is the surface roughness and the profile form deviation, what we have to achieve. And there are the dressable tools, we can achieve much better values than with the electroplated one. That's coming out of the manufacturing process. Also, to find the right CBN grain size for electroplating, it's a little bit more difficult for the vitrified bonded CBN, where you can also make a mixture of different abrasives, grain sizes, and then you can also have the strategy that you dress them a little bit with speed ratio to achieve your surface roughness and profile form deviation, what you want to achieve.
Thank you, gentlemen. Next question is, how do you decide how much stock to remove per pass?
All the stock in one path.
No,
That's what you commonly do in high mass production automotive, truck, and even industrial gearbox grinding, at least in the bevel gear world. In the worst case, if you, for example, have free quenching or something, that you have the gear is rather looks like a potato chip than flat, so you have to fight with some distortions from there, then you do a dual rotation. With a dual rotation, you take more than 75% of the stock first, and then the remaining in the second path.
You have a given Q max for a given combination of grinding wheel and dressing wheel, and from this Q max, you can the Q max is the material you take off, the volume you take off in 1 second.
Zeitspanvolumen.
Right.
Removal rate.
And then you can calculate the feeds and speeds and also the number of strokes. So do we.
Thank you. Next question is, if certain harmonic mesh frequencies in ground cylindrical gears are excited, where do they come from and how can they be eliminated?
You got the first harmonic. That comes from the tooth impact frequency, from the tooth mesh impact frequency. Then you got the second and the third harmonic. They're mostly related to the tooth impact frequency, or let's say the flank form, the profile. If you had higher harmonics, there could be ghost harmonics coming from your manufacturing machine. That is a possibility. But in particular, it's surface finish. You sometimes see, depending on the dressing or something, you see in a cylindrical gear up the profile, if you look under the microscope, you see 6 or 8 streaks. And you find a 6 or 8 harmonic, and it comes from that. There are scrambling effects possible, like for example, we do something in the threaded wheel grinding that while we grind the part, we shift it a certain amount. And with that, you scramble the surface, and you can eliminate those effects. In bevel gear grinding, there are also effects like that possible. But the higher harmonics above the third or the fourth, Sebastian here is actually a frequency expert for grinding. He says everything, the fourth is a borderline thing. Everything above really is surface related, and everything below is related to the form of the tooth, to the geometry of the tooth. First, second, third, you can with high conjugacy optimize your crowning, get your impact. Maybe you put some wanted twist on or some entrance modification. You can get the first 3 harmonics under control. But with that, you will still have the higher harmonics, and actually higher harmonics that in the past were of no importance. Now, with in vehicles, for example, hybrid vehicles, electric vehicles, quieter engines, those kind of noises, they are much discussed in the past couple of years, because in the past before that, they were not really interesting. People ignored them. They were not so important because there were other noises.
But the important thing is we can eliminate it with the generating grinding, and we can also give a real, a special topological flank. So let's say we can do the left flank, we can do twist free. On the right flank, we can do the counter twist. So we have a lot of play area.
Thank you. This next question is about some of the new types of grinding wheels available, and what are the advantages of the wheels like the Cubitron and the ZGX that have been introduced recently?
Cylindrical people should answer that, because I think there was way more success in applying them to cylindrical gears. In the bevel world, we're just picking up a little bit, but it's not really flying. It's not really that of a breakthrough so far.
The situation with this new type of abrasives, however you call them and however they look like, is the aim is to improve the metal removal rate, to higher speeds and to cut more stock in one cut, so that you do not 3 passes for grinding a module 6 or 7 gear, that you can make this gear now in 2 passes.
On the contrary, with these new abrasives that are cutting more, you, let's say, have not the same roughness result as you could have with standard ceramic wheel, where you can really choose the type of grit you would like to have.
That's the experience we did too. We can, if you have a lot of stock, you can eliminate one roughing stroke, and you even can improve the feed rate during roughing. But the roughness afterwards on the gear is, let's say, RA 0.4 and bigger. And this is for some customers not acceptable.
And another limitation, sorry, please.
No, the other way is you can choose a smaller grid, not the 81, the 120, and they told me that these have the same productivity, but it's smoother. But I cannot believe this right now. We have to prove it again.
Yeah, just a comment. If you have to go to fine pitch gears, this result is even worse in terms of roughness and capacity of really improving the the feed rate. This is more related, I would say, below module 2, something like this. You can have some results in roughness operation. Over, sorry, not below, over module 2.
Thank you. This next question is very specific, so I hope somebody will be able to answer it. But there's a publication showing a purposely wavy ground profile in order to match it to a mating member with certain profile imperfections. Is this a new way of grinding quieter gear sets?
I think somebody from Liebherr should answer that. There's a patent out there. I remember that.
The situation is the following. It's this modification is not new. There are some doctor theses out of the FZG Munich to grind this periodic waviness on the tool. You can do this with the old mark machines, for example. You also can do this by dressing your worm, your grinding worm, with a point-by-point dressing method. That means you make a topological correction on the worm and you grind with this. At Liebherr, we find out a way that you can grind such a modification on a gear with a conventional dressing tool, what you use also for axle grinding, and by do some dressing modifications and grinding in a diagonal mode, then you can create these, we call them neo-modifications, yes. But as Dr. Stadtfeld said, first order, second order, third order force, higher orders, not so easy to handle this with this method. No.
Thank you. How important is the setup of the coolant nozzles and the volume of oil supply in the grinding zone during grinding?
I can answer that for bevels, maybe, more specific for bevels. Because I have actually written a grinding paper that really makes a point that sometimes less is more, and it's important where the nozzles go. So we have developed lately a system with laminar flow nozzles that have a certain diameter. They are pressed flat at the front for a certain length, and with the pressure and from the coolant supply, you receive a laminar flow out of the nozzle. The laminar flow can bridge larger distances, and you can direct it, for example, on an IB inside of a grinding wheel or on the OB outside of a grinding wheel. Then we use, in addition, where the grinding wheel comes out of the grinding zone, we use a spark extinguisher on both sides, on the inside and outside of the profile. Because if there are sparks, they would take a whole revolution, and that is time enough for them to burn in the in the ceramic base. And then those chips, those metal enclosures, they would go a second time through the grind. So there are laminar flow nozzles at the intake before the grinding zone. There are laminar flow nozzles with a certain volume stream at the exit for spark extinguishing. And then at the opposite side of the grinding zone, there's a high pressure that's normally, commonly 40 bars or so, a high pressure coolant, a grinding wheel cleaner, where jets perpendicular go to the grinding wheel and wash out the pores of the grinding wheel. So I think that that system actually, we supply that to customers with the idea that you change the whole frame, which you have set up with, what did I say, 1, 2, 3, 4 at least, and then the fifth would be the high pressure, and you take the frame off and it's labeled with that job name. Because setting up the pipes like we had the flexible plastic pipes in the old days, that is completely unacceptable, and that is trial and error work. And in a mass production, that is not really the way you would like to work.
Would anybody else like to add?
Yeah, in generate grinding, it's a little bit more difficult because under the oil beam and also there's this nozzle we have running through a threaded worm. That means it's not so easy to optimize this situation for the left and the right flank, because at the end the complete worm is running through the nozzle. That means you hit them all, and therefore we always try to reduce this to a minimum. The situation is what you get from your suppliers for the cooling units, and the next is if you start to reduce this and you get a little bit more firing spot in generate grinding, all the customers said, "Ooh, I don't want to have this, and therefore please turn off the pipe again and make as much as possible."
And you know, we take this so seriously, And it might even be one of my side hobbies, because I see that people pour, in the old days, you know, we had big nozzles and flushed the oil and really poured it over. And that is actually what the workpiece sees. It's just a shower with air bubbles. So it sees air in the contacting zone maybe. So we take that so seriously that those laminar flow nozzles that I talked about, they have a laser setup. You put a laser head on, and the laser beam points exactly at the spot that you can predetermine is the grinding zone. So it's even a little sophistication for setting up of coolant nozzles.
Thank you very much. Here's a related question. Is it possible to grind gears at a high production rate without the use of oil or coolant during the process? And if so, can it be done without thermal damage to the part?
Of course, has been shown at the EMO show.
This is only can you answer.
Enrico?
That's our answer related to the previous question, how important is the oil nozzle? Not at all. No, that's the solution we are proposing for high production of cylindrical gears. So basically, it's the dry grinding process is existing since many years with like MAG machines, but not in a productive way. And the reason why is because roughing operations with very high removal rate is not possible with a grinding wheel without the use of oil. So the idea of combining on a same machine a skyvogging operation that is doing the roughing process and the grinding wheel, which is just taking out the scallops left from the skive hob tool, really give the possibility to not thermal damage the part and being at the same time high productive. An important thing to consider is that this process has really, in terms of tool cost, not at all a big influence in comparison with the standard grinding wheel with wet process. It's even a little bit lower because the skive hobbing in carbide typically can be used as a roughing process, not as a finishing process. So can work even more, and we spare a lot of cost of the dresser, which has a much reduced work in comparison to the actual wet process. So, please.
One question to this dry grinding. How do you get rid of the chips sitting in the pores?
That is in?
How do you get rid of the chips that are sitting in the pores of the grinding wheel? How do they get out?
The chips in the finishing pass, first of all, are not so much because we are just cutting a very thin layer, so there is space in the grinding wheel. And by the way, we shift during the process so that each time we are cutting, we move in a new part of the wheel. So there is no real need of making or taking out the chips from the wheel, because we just make a finishing pass and we shift during this finish pass on new wheel.
Thank you very much. Are there any more questions from the audience?
Beveloid gears grinding. There is a difference on one side, cost side, and drive side in the surface finish. The cost side is really roughing. What can be done, because it's a different. And also, how good the twist compensation work for beveloid. So, if we compare beveloid and spiral bevel grinding process, which of these designs is easy to control the surface?
You know my answer. Of course, you should lose the spiral bevel with a small cone angle. No, the real answer is, I think the cylindrical colleagues should answer that. But there is a version that we call hypaloid, like it's an artificial word. It's not a beveloid, because a beveloid, by definition, is a conical cylindrical gear. Really give the real answer, because he was asking for beveloids, not for hypaloids.
Would Would anybody care to add?
Do you know how, in general, the Beveloid have a lot of negative lead crown? About 60, 70 microns. And so we have to check whether we can compensate the twist with this huge lead crown. I think this is one main thing.
Thank you. Are there any other questions from the crowd? In that case, I think we are going to wrap up our first session of Ask the Expert Live. Thank you all for joining us, and thanks most of all to our experts for providing the education.
Thank you very much. It was fun.
Thank you, ladies and gentlemen, for reading us at Ask the Expert Live. We'd ask you to come back at 2:30 for our next panel discussion. Otherwise, enjoy the show.
Thank you very much.
Thank you very much.